What I'm reviewing in this video is a 1 kVA isolation transformer. I'll go over what reasons you may need to use one. We'll look at what modifications are needed to truly isolate the output, what's the outcome of those modifications, what design choices I'd change, and what needs to be done to fix the power tripping issue I found. I've purchased this AC isolation transformer. Just received it. I need it to do various testing on different sorts of power supplies and things like that. I primarily got it so I could isolate the equipment under test so I don't blow up my oscilloscope or any other types of equipment because of certain ground feedback loops that exist. Of course, having purchased it, I'll just show you, I'll switch it on. What I found is that the output ground is actually not isolated from the input ground, which sort of defeats the purpose. So I need to spend some time to open up the box and fix that grounding issue so that for my implementation, what I need it for, I have a fully isolated output, including the ground isolation, so that I don't have any issues when I test my equipment. So I'll just switch it on so you can sort of see what it's like. So it's counted down and now it shows an input voltage and an output voltage. This model doesn't come with a regulator which sort of helps make sure the output voltage stays within range, but didn't need that feature, wanted it as basic as possible. So as I use it, as the load will draw a certain amount of current, voltage, whatever, that will be able to be displayed here, which is a good little bit of feedback. Now, let me switch this off. Showing you the back. You can see there's two outputs, both the same. It's just a matter of providing that. I do wish in hindsight that these were on the front, so it's easy to plug in and out. But for its actual application, I think, or the way they built it was to use in a certain environment, you plug it and you're done. Not necessarily something on a bench to plug in and out, twist things you want to test. So let me show you the wiring and the isolation issues that I have. Okay, so I've unplugged it. And what I want to show you is how the grounds are all connected here. So here is my mains power ground. You can see if I go to my ground here, it's connected. Also here, you'll see they're connected directly. And these are, I think, also connected. Okay, but at least these are not connected. So if I touch on one of the live pins or neutral, you can see there's no conduction. So that's going through a transformer and there's no direct connection. It's isolated in that sense. Okay, so it's just the grounding that goes through from input to output. So what I need to do then is open up the box, look at the wiring, and then separate the grounding on the output so I have a totally isolated output so I can do my testing. I wanted to give a higher level idea of what the isolation transformer is supposed to help with. And here's a very basic schematic diagram showing of a typical configuration. We have the isolation transformer, we have the device under test, we have an oscilloscope as a piece of test equipment, and you see the power sockets of, say, the isolation transformer, and then you have the device, now being the oscilloscope. In the house wiring system, the ground and neutral are actually connected together. So I'm just representing that here with this sort of connection. And so when the isolation transformer came in new, it has this ground connection here as well. Okay.
Now, as a device under test, it can be many different types of structures. It could be a metal case, could be a plastic case, many different ways, a lot of what ifs. But let's just assume worst case in the two scenarios. So one, we have a device under test with some circuitry. We have some grounding plane or ground reference within the circuits. And we have a ground coming in from the isolation transformer's output as it wouldn't been as purchased, right? So in this scenario, generally what we're trying to avoid is blowing up our test equipment or potentially electrocuting ourselves through various ways. But the key thing for what I am intending is the use of an oscilloscope under testing devices without damaging my oscilloscope. So a typical scenario is here. We have a positive probe of the oscilloscope where you want to touch somewhere inside the circuit. And we have the ground clip of the probe, right? So under this situation, when you're powering something like this and you're not doing anything to it, like probing it, there's no problem by connecting it with this ground in place. And even as is, when there's a scenario where you've got the ground that's coming in, and generally the ground is either connected to the chassis, or if it's a plastic chassis, you'll only have maybe 2 wires, you don't even have a ground. And you have the live circuit, to that 240 volts coming through. It may go through some circuitry, some regulation, whatever, rectification. This could be for line voltage, or it could be 100 volts DC, 50 volts DC, or whatever it might be. So in this type of situation, if the PCBA is not grounded to the chassis, then there's no problem. If I get my probe and I connect it from here and click here, and I happen to hook up to this part of the circuit, you see that this is still fine, even if I connect the ground probe to the live power. Now, I might do that because I want to have a ground reference and probe somewhere else. So I want to have a reference point, be it a ground reference to my scope, but it's not ground here. And since this is floating, nothing blows up. Because as you can see, if I go from here, and this is the path of the ground, right? It goes all the way here, it comes all the way over here, it goes through here, comes here, goes through ground, comes here, and then stops here. And at this point, the neutral is not shorted to the live wire, right? There's no short here, so there's no problem, okay? Now, and I mean, there's no closed loop, so there's no surge of current through the oscilloscope probes and nothing is damaged. Now, if this happened to be connected to the chassis, let's say the ground plane of this device is connected to the chassis, like that. Now, what would happen if I connect the ground of my probe to some high voltage point? Well, now we have a bit of an issue. Now we have this loop, a closed loop. You see, the path is now fully open. Now, connecting through the chassis, I've come through here, I've come to my ground, and now I've essentially shorted to my neutral of my mains. And that's essentially just shorting these two together, which you can see is going to cause a big bang, huge surge current, lots of damage probably. So we don't want that. Now, if we take the scenario where this ground wire is actually cut, so to take this wire here, and we've cut the ground, which is essentially what I did, okay? Now, with the probe here, ground reference at the mains, what we see now is that the ground path has been broken. There's nowhere for the loop of the current to flow. You see, we're stuck. And because of that, we don't have a short across the live and the neutral. And that's what we want. We want to be able to clip the ground probe of the oscilloscope anywhere in this circuit without causing damage to either the oscilloscope or the device under test. That's the key reason that I'm using the isolation transformer for. Hope that makes things clearer.
Let's open this up and see what we have inside. Okay, look at that baby. That is a huge transformer. That's great. All right, just taking a look here, what do we have? We have the output sockets, which are just tied together, so they're shared. That's basically the blue and the red. We have the ground, which you can see goes across the front, carries through down to here, seems to be soldered to the case here, and that goes to the mains cable as well. All right, so here we have a controller for the display. This seems to be a little control board as well. Here we just have the power switch that turns on and off the power. And that's about it. So I'll want to do probably minimal change to this. That means I don't want to pull apart all these wires, and I'll try to take a look at what that control board's about. But essentially it seems all I need to do here is remove this wire from these output sockets. Just to cut this maybe, or actually down here, because as I'll show you later, maybe I'll show you now. Okay, if you can see, it's not blurry. You see the ground comes down here, attaches itself to the base, which seems to be soldered, and there's this screw here as well, maybe a pin that's grounded in there. Yeah, and then that ground also goes to this forward part, which I'll take a look at, but I believe it's for these boards. So just removing this connection here should do the trick. As I've been probing around in the box, I came across this little screw here, which is one of the feet, right, that's come through here. As you can see, it was actually rubbing on the wire. This is the live wire from here. It comes through here, the live wire. This is it here, and it goes through up here to the switch. Now this wire is on this screw. Not loving that. I mean, a bit of vibration over time could cut through that plastic. And if I rotate this around, you can sort of see already there's some rubbing marks on the wire. Okay, so yeah, it may never happen, but I don't like that. So I'm going to have to put something on here to stop these wires from even touching this screw. Small little things like this make a difference. I have done a little bit of looking. So this red wire and blue wire here on the output, the red wire comes all the way through here, goes through to the back of this board, which I assume is behind this relay, and essentially once the power goes on and this thing settles down, it then switches on the relay to connect the output wire, the red one, to this one up here. So this goes all the way back in here, goes through the switching circuit, comes back, and then up here. Many of these wires here are sensing wires, like sensing the input voltage, the output voltage. We have 4 wires on the primary. There's also a 10K resistor here across the ground and output voltage, the main lines. Whether I cut this, let's see, the easiest thing is to cut it or desolder it. I think desoldering is going to be hard since it is such a heat sink. If I cut it, allowing to maybe around here, so if I want to put it back I can, but I will cut it here and then seal it up so there's no floating wires. And at the same time I'm going to fix this thing here to put something around this. Need to think about that. Okay, that's what I wanted to share right now. I'm going to switch on the voltage just to show you how the measurements are before I make the change, so you can see why we need to do it. So, okay, voltage is switched on at the front of the unit. I have to be very careful because this is dangerous voltages and everything is open here. So you look at the input voltages with respect to ground. So the red one, get my hand out of the way, 240 volts. You can see the blue one, it's got 3 volts, so essentially 0. Okay, and then between the blue and the red we have 240 volts as well. Now I want to show you, if I touch here, and the case is the same. Touching the case is the ground, which is the same as the input ground as well, which is also the output ground. Okay, looking at this ground wire, I'm going to cut it here. Just like that for now. I've just put some heat shrink over this one that I've cut here and here, the earth, and a little bit of heat shrink over this screw here. A bit hard to see from the top, but that's covering the screw and it's not touching the wires anymore, so that should do the trick. Okay, I wanted to show how this isolation transformer is now isolated from the mains, ground, etc. So I just wanted to show you here, it's off at the moment. I'm going to switch it on and you'll see this is plugged in here. These wires are plugged into the isolated output. So if I switch this on, you'll see that there will be 240 volts coming out of this. Okay. Now, none of these outputs referenced to ground. All right, there's just some 16, there's some ghost voltages floating around. That says 217, but that's also a ghost voltage. It's not 240. Now, I'm going to switch this off. You can see it's off. Now I want to connect this. This is supposedly live to the ground. So now this ground will be connected to the mains ground through the power cable of the transformer, isolation transformer system, which is grounded. The chassis is grounded. Now when I switch this on, normally this would blow a fuse, but because the output is isolated, when I switch this on, this normally being ground will now have the voltage. So I'm going to switch this on. Okay, the power is on. Now I'm going to put the ground here and this on the neutral pin. You can see there's 246 volts now. Okay, and this is the same if you swap these wires around. So basically, once I clip the live wire or the neutral wire from the isolated output to a device's ground, that ground then becomes the reference, that device's reference, with respect to the other. So now this is not shorting to ground if I was to put this on a tested device. So that's what we sort of want, right? We want to be able to test things without worried about where the power is connected or where the ground on my oscilloscope is connected. So when I connect either one of these to a device, the ground of the oscilloscope won't be shorted to any of these terminals, which is not a good thing. I wanted to make some short comments about the overall quality of the product. And before I do so, I just want to acknowledge that it's bought from a Chinese manufacturer, and without them being able to cost down these products like this, I probably wouldn't have bought it. I probably wouldn't have spent so much money that would have normally have costed to buy such a thing. And so I just want to acknowledge, although there are some cost-cutting things I want to point out, I do acknowledge they need to be done in order to bring the cost down. So it's no criticism on that. I just wanted to highlight some of the things that would have been nice to have starting with the fuse here. This fuse is a special type of electrical fuse. I will pop up a picture in the video for you to see it. It's got a built-in fuse. The thing about this switch, it is, I believe, rated for 10 amps, and anything above that, it'll trip. Now, the issue is, with the 240 volt supply, this transformer can really only take about 4 amps. If it was a 120 volt supply, it would take 8 amps. So, given that, if this was delivering or having too much current pulled from it, it may not actually trip. So, ideally, I would have liked to seen an option for the fusing here. And I may actually put some fuse rated at about 5 amps on the box. Might have to rewire a fuse in here down the track. The power switch as well is a single pole, single throw. It's only switching the live. Just for extra safety, it would also be good if this was a double pole, double throw, switching off both line and neutral. And the other thing is, you see the quality of the wires here being basically soldered on. So as you've seen in the picture I popped up earlier, these red wires that go to the back of the PCB here, they're actually soldered to the back of the board. Not great. Would have preferred a proper connection somehow, maybe some terminals on the board with some clips. That would have been a much better way to connect the wires as well. I just wanted to highlight these few little things that I'm picking on. I think I previously already highlighted about the quality of these terminals. Yeah, I think one here I've covered up, and then there are these others, the bare, which is fine, but it's just how they intertwine with the wiring. It's good to keep things safe. Yeah. So other than that, you know, it's a pretty good product. Like I said, it's relatively new, and I've still got to put it through its tracks about how much it performs, but I'm assuming it will be okay. For this video, just highlighting the initial impressions. Okay, I'm going to put this back together now, and look forward to using it. Okay, this is done. Okay, I'd like to try and demonstrate how sometimes when I switch on the isolation transformer, it's fine, and then sometimes it trips the power. So I'm going to do this and see how it goes. Okay, this one worked. Nothing has to be connected, it's just a matter of when you switch it on, and I believe it's depending on when the cycle of the power in terms of the sinusoid, right, 50 Hertz. If this happens to switch on at the wrong time in the cycle, it has maximum surge current and it trips the breaker within the room. There you go. See the power's being tripped? I'll switch it off. Switch on the power again, reset the switch. Try again. It's okay this time. Okay this time. And again. So you can see it's quite a matter of luck depending on when you switch it on, whether the power is going to go out. So I'm looking to actually build a surge protection circuit for the unit so that it doesn't trip the power, something that will limit the inrush current and then switch out the limiting mechanism so that it comes back to normal operation. So that's something I might look at doing in order to use this effectively, because I don't want this tripping my oscilloscope every time or my equipment that I might have set up. The power goes out and I have to wait for everything to restart again. So I'm going to address this first. It's a bit of a pain because I have a number of projects I've been wanting to do, but now this isolation transformer becomes a project in itself. I will probably do the more surge protector circuit as a separate project and a separate video. Right now I just wanted to highlight that this is something I've discovered for the product as a part of the sort of review I'm doing here. Thanks for watching this video, and yeah, I'm looking forward to using this isolation transformer for a few projects. Please do subscribe, leave any comments, anything that would be awesome, and I'll catch you around. See ya.